All right. I think we're live here. I haven't done the OBS to YouTube flow here yet. I did it with Twitch with my new setup this week on the Upbound channel. But I think we're all set up here. If anyone is watching, which I'm not expecting that many folks to, first stream on this channel and just posted about it on Twitter. But hold on. Also, let me check I'm getting a warning about video resolution here saying it's not optimal. Okay, well, as long as it works for now, that should be okay. But anyway, yeah, this is a new channel, and if you've read any of my like writing or anything like that, then you're likely familiar with the fact that I really am passionate about hardware and specifically RISC-V. So I do a lot of writing about that. And I've wanted to, for a while, implement my own CPU and then kind of like build a software ecosystem on top of that. And I have kind of like a nascent project around it. But one of the things that is really important to me is that I feel like that building hardware, understanding hardware, kind of like going to beneath the operating system, maybe would be a good way to say it, is kind of a more opaque area for most folks, right? There's lots of resources for becoming a software engineer, and I'm sure there's things in hardware, right, that I'm just less exposed to. But for me personally, at least, I didn't study electrical engineering or anything like that. And so the barrier to entry feels a lot higher, in my opinion. And if folks don't feel that way, then obviously like would love to get more resources to share with folks. But I've kind of struggled with starting and stopping on this project for a while. And one, I really want to make progress. Two, I think there's some interesting ideas I have for what this will look like in terms of like actually being useful in some sense. And three, which may be most importantly, I want other folks who want to do similar things, want to get involved in hardware, to have resources to be able to do that. So that's kind of the motivation for starting this. This is obviously our first stream here. And so if this is something you're interested in, like, please let me know in some form. I'm not super concerned about subscribers or things like that at this time. But if it's useful, feel free to ping me on Twitter or anything like that. I think that's linked to this channel. And let me know. And I'm going to keep making them as long as I can, as long as I can find the time. I'm going to keep trying to improve the streams and things like that, and improve the project. But today's just going to be kind of like an introduction to what I have so far. We're going to look at Vivado, which is Xilinx kind of IDE, which a lot of folks are not big fans of, but Xilinx basically makes FPGAs. I have an FPGA board, a dev board here that we're going to use for the project. It is the RDA7. Okay, that looks pretty cool with the camera. Yeah, nice. That's pretty neat. So this is the RDA7. It is a dev board from Digilent. Not sure I'm saying that correctly, but it has an FPGA on here. Let's see if I can point it out right there. And it also has a bunch of peripherals, obviously, as well. So we're going to use this. This is really the main FPGA dev board that I use. I do have a couple other dev boards laying around here that we'll continue to explore. But that's what we're going to use today. That's what I've used for this project in the past. But like I said, this project is very early on. So we're just going to explore it, get started, and then see where we go from there, see how much interest there is. Alrighty. So let me actually pull up some interesting stuff here, and we can get started. And I'll move over to actually showing my screen. All right, so I've got my dev machine here coming over the NDI plugin. So the name of this project is Moss. The name, I need to write down where what exactly the motivation is for it. But it's a couple of different things. And you can see here that this project has been around for a bit. Let's see what the oldest commit is like. Oh, we're looking at 9 months here. I think the oldest commit is a bit older than that, but it's been around for a little bit. But I haven't really been able to make super meaningful progress. I can show you today actually using the UART to be able to send messages between my dev machine and the FPGA, or from the FPGA, I guess, rather, to the dev machine. And we can just talk about kind of like what it means to configure an FPGA. But yeah, so there hasn't been a ton of work on this yet, but there is some basic structure. The name Moss is inspired by like moss itself, like the I don't know if it's a fungus, but essentially the idea of it's something that is very simple, but kind of like offers a lot of life from it as well. I'm not a biologist, so that might not be the best description there. It also has some nice qualities. I like that, open source software with OSS there, operating system, etc. My last name starts with an M, but I don't like when people name things after themselves. So that is not a motive. That's an explicit non-motivation here. But anyway. Also, if folks are interested, feel free to drop stuff in the chat and I'll check in on it from time to time. I'm using YouTube because I know a lot of folks use Twitch. Like I said, I used Twitch this week. YouTube by default is saving the videos for me, which I know you can like sync videos from Twitch to YouTube, and then you can also do clips. I guess there's just like different styles, but with my motivation being that folks are able to use this as a resource. I really want all of it to be preserved, which might make it hard to consume. So I'll cut it up as necessary for folks to have resources. But yeah, I kind of want to show that I struggle with this a little bit. And I hope that watching me do that might open the door for other folks, but who really knows? We're going to see how it goes. I did want to talk about a few different resources that I find really useful. So let me grab these off the other table here. Hey, Siam. Thanks for joining. I just dropped in the chat there. Definitely inspired by folks like Siam who have awesome audiences and folks that follow them and check out their content. So I'm just doing my best over here, learning from folks like you. Okay, so I'm going to go back to the main screen here. But one of my favorite resources, and this is not specifically to hardware, but is the XV6 operating system. And it kind of, with the new RISC-V version, it has a lot of useful information. I actually printed out this book, which, is probably not the greatest use of resources, but I've taken it around with me a lot of places and annotated it quite a lot. I also have my favorite book of all time, Computer Architecture, A Quantitative Approach by Hennessy and Patterson. This is the most useful book on hardware I have, or I guess on processor design, really, that I have ever read. And if you took any classes related to this in college or anything like that, you probably used computer. Whoop. You can see my streaming etiquette is still a work in progress, but you probably use Computer Organization and Design RISC-V edition, or you might not have used the RISC-V edition, but that's the latest one. And it's kind of like a gentler introduction. There's a lot of things from the second book there, the gentler one, that are in the index of the larger one. So could have used either one. Great resources there. Kind of things that have taught me a lot about computer architecture. So awesome. And Jonathan's here. Thanks for joining, Jonathan. Hope you're having a good weekend. Appreciate you stopping by. All right, so let's get back actually into doing things here. All right, so this is Moss. Right now, I have some setup for Vivado and some config files here that basically tell it how to configure the RDA7 board I have here. This is pulled from this Digilent repo, and you'll see you kind of uncomment things that you want. So a lot of this is commented out. I have the switches here uncommented, which means that I can access them in my Verilog design. So the switches are going to be these things down here at the bottom. And then I also have the clock signal and the LEDs and the buttons. So I have a number of things accessible here. And I've been using these for primarily just this UART implementation. So this is sending from the FPGA to the dev machine. And you'll see here that I actually implemented with this in reverse. And that was because whenever I did this, I was having trouble getting it to print over the serial console with the correct ordering. So I just stuck it in there. I think I was doing a demo at that time. I have since corrected some of that, which we'll look at that today. I have a very simple ALU here as well. And you'll see it's basically doing 4 operations and or add and subtract. And we don't have to actually put these things onto the FPGA to do simulation. We are using a very popular framework, Verilator, that uses C++, which I'm definitely not a C++ expert here, but we're using it to be able to run some simulations, and we'll talk about how that works a bit. Yeah, so there's you can instantiate just the module. It looks like here in top we're not actually doing anything, but I do have some examples locally. So anyway, I'm gonna open up my editor here to show you actually a bunch of stuff that is not up here quite yet. Alrighty, so you're gonna see a ton of stuff in here that I've just hacked on over time. And so there's like the beginnings of an operating system that doesn't really do anything quite yet. I think this was from a blog post that I was writing at one point. Some linker scripts. We actually have some different stuff here in top where I was using the ALU. And I'm certainly not a Verilog expert, so I'm going to be on these streams kind of improving my skill set there as well. I'm going to make this a little bit bigger for folks. And some random stuff around using WebGL to create a visualization of this. Toolchain stuff. You can actually see how some of our config changed here because the ALU was added in, and we're going to open up Vivado here in a moment. Have some contributing stuff, and yeah, so most of the ALU stuff hasn't been actually pushed up, so maybe we'll get around to doing that. I do have a make file to do some of this, and like I said, so we have like a bunch of stuff that's in progress here, and not really in a great state. You'll see that I'm using RISC-V for doing kind of like the software level stuff. I haven't made the decision whether I want this to be an actual RISC-V CPU or rather just that it's something we implement ourselves. Obviously, using the RISC-V specification is going to allow us to integrate with other software compilers and things like that. So I think that would potentially make sense here. Cool. Yeah, so we're just gonna kind of get started. Like, this is obviously very unformed. I don't even know exactly what the mission is here quite yet, which is a critical part for building productively. But we're gonna do all of that on the stream. Just gonna kind of stop putting that off. Also want to mention we have some docs here. Only this protocols one is pushed up at this point. And yeah, so it has some information. Basically, I just want to produce as much content as possible for folks to be able to follow along. So there's like random stuff on C, C++. I'd like to do some work on, defining how power comes into play with processors. And that's an area that I don't have a lot of expertise in. I did move this JTAG stuff out into its own document here, so maybe we'll push that up. Have some firmware stuff, have some things around logic design, power management, just terms. There's so many terms in hardware, probably even more, or maybe I should say in computer architecture, probably even more than in software. So that's also a goal here. And then writing some stuff around Verilog. I try to link to anywhere where I pull information from to make sure I'm giving attribution. But yeah, so all of this is meant to kind of like serve as a resource. So today, I think it would be fun to get back into just kind of like the workflow, right? How we get things set up. And as we go along, since this will be on stream, it'll be something we can reference back and check out. So yeah, should be a lot of fun. And we're just going to go and see where we end up. So I'm going to take my my FPGA here, go ahead and plug it into my dev machine. All right, so I'm just using this to be able to do that. I guess it's a, what is this, USB-C to USB-A cord here. Not actually sure that's 100% correct. All right, but I'm gonna plug this into my machine. All right. I don't know if it's gonna reach up here, but we can see that there are some lights lit up on there. Let's see if it shows. Yep, so it's getting power. So that is a good sign. One of the things I did pretty recently is do some work around discovering USB devices. And that was in a different project. So I might want to move some of those docs over here. Let's see if we can do some I don't know if to call it hardware because we're kind of like designing hardware to some extent since it's a processor, but it's a soft core CPU. So let's say boards, and we can keep all of our documentation here. I don't know if we yeah, so it looks like we don't have too much here. So as we go along, we can add some links to necessary stuff, just so folks can find it as well. So RDA7, and let's jump into, I'm just going to use, I need to get this configured to not show all of my search history here. All right, so this is the RDA7 Digilent reference here. So no, I don't want to do that. What is this link? Oops. Let's grab this. put something about reference documentation here. Actually, let's just do that. All right. And yeah, so you can see all kind of the specs here. We're using the 35T edition. One of actually my most popular blog posts here is let's see. Well, that is really outdated. I think it's on the second page here. Yeah, installing Vivado. This gets the most hits on my blog. This is when I first got this dev board. And yeah, it's how I set up Vivado. So maybe we should actually link to that. A dev here. And let's get something started for Vivado. And these are things I'm going to clean up before pushing any of it, but also, what branch am I on? Fix reversed UART. Yeah, okay, so this is the most recent thing I was doing. So if we hop over here, we have, that's our sim. I want to get into RTL, and let's actually just go ahead and talk about the fixes here for the UART. I mentioned that I was printing backwards, and we want to do this instead. So our change here was, I believe that I went from the word index and bit index being the beginning and instead being the end. So, oh yeah, and then I did the for the registers here instead of going, wait, what did I have before? Yeah, instead of going from 1 to whatever the total bits here are, I went from 0 to the total bits. So anyway, let's get this started because I know a lot of this is like newer things, especially for folks who aren't as familiar with Verilog. I'm not the most familiar, but I do have some experience. So I believe can't remember exactly how I started this up. I think, let's see, let's actually look here and see if I have it in this blog post. I haven't opened this in so long that I can't even remember exactly. Yeah, okay, so tools. Tools, I believe it's in Xilinx. Vivado, bin. Let's grab this and just add something to our docs up here. One of the big things that, one second. Guide referenced above. I also have this contributing docs. So I'll need to think about kind of the desired what goes in contributing. Probably just like high level, like this is what you need to be able to do to open a PR and get it merged. All right, so let's go ahead and do this. And it looks like this is working potentially. Maybe it's working. Also, I'm a little, yeah, there's start GUI. Okay. Yeah, it's coming up on my other screen here. There we go. All right. Moss, toolchain, boards, Homedan, GitHub. What is the difference between these two? Oh, Moss Computer and Moss Comp. Moss Comp is the, yeah, that's the shorter name that I used. All right, so this is what Vivado looks like. It is not the most beautiful thing ever. Also, I'm going to have to come back around and see if this is even really, you're even able to see it at all, really, on this YouTube stream, because of the low quality of this coming over the NDI plugin. But essentially, it's using the config that we have in toolchain here. So it's able to identify those things, and when we make changes, it's going to be reflected here. The thing that, or one of the things I don't like right now is that it's using my local path here, which is not going to be acceptable. So we're going to need to fix that at some point. I think I have an issue open on Moss here that is, yeah, parameterize Vivado XPR files. All right. We'll let that run on a separate one here. Okay, so since I have Vivado open, let's look at what's in here. You can open that up. So basically we have two editors going here. I don't really love using the Vivado one, but that's okay. And yeah, so we're implementing the UART sender part of this, the TX part. Let's actually look into I think I added some UART documentation here, which one of the things I need to improve on a bit is not jumping around quite as much. But so it's not a protocol, it's a physical circuit. And so you have two wires kind of sending and receiving here. And if we look into, let's see, where did we have the XDC file here? LEDs, buttons, USB UART interface. So this is how we're actually able to send things. And so RxD out, I think I put a note there. But it's a little bit confusing because you have the FPGA, which is sending, but the receiver is actually this, I'm going to need to look it up here again. Well, let's just look at the reference. Like I said, I'm a little, I am a little rusty on everything, but FTDI, that's what I was thinking of. So FTDI, you know, let's actually just like use Brave or something because I don't want my search history coming up. You can see some of my local Upbound if you want. So let's actually just use this for everything. So FTDI here is a company, but it's also kind of an interface. So USB to serial UART interface. So if we look at the already here. It's not very big, but oh, here we go. Perfect. So let's look for the FTDI. Okay, so shared JTAG USB or shared USB JTAG UART port. So this is 2 here. That's the port. That's where we also have our power coming in here. So we have our, I can switch this over momentarily. We have our power coming in down here. And then 18 is our flash memory. And then I believe, I'm just looking at this behind the scenes. Let's see. It doesn't actually show it, but I can look on here. Yeah, you can actually see it if you look really, really close. It's not actually labeled on the reference manual, but this is our shared JTAG, our USB JTAG UART port, where we're also giving our power. And then right above it here is the FTDI chip, and actually says FTDI. I don't think my camera is going to be able to handle me putting it super close, but it says FTDI on there. And basically what it is doing is translating the UART that we're sending to it, the signals on the UART to USB, which are then going to our host machine here, and then are eventually going to come to our serial console. Also, should mention, anyone in the chat here, definitely feel more than free to correct anything that I say. Like I said, this is kind of like a vulnerability thing for me as well. Something that I have a lot more knowledge on than a lot of folks that I'm around all the time, but a lot less knowledge than folks that work on this all the time. And one of the things I want to do here is show that, that's okay. And we're going to learn together, and me learning is going to help other folks, I hope. All right, so we have this 35 version here, and FPGAs are mostly made up of lookup tables and flip-flops, and we can definitely talk a bit more about that in the future. But this is how you're able to dynamically configure it with different circuits that you're building. So that's how we're able to actually do this UART module. Cool. All right, so let's actually just go through the process of flashing this onto or programming the FPGA. All right, so we have the UART stuff set up, so this looks fine. And I have the update. And we'll talk about the actual UART protocol here. Let me make this a lot bigger. And what we want to do is run synthesis, implementation, and then generate the bit stream and program the FPGA. The programming is also happening on that USB UART interface, and that's using the JTAG portion of it. So we have UART and JTAG is two terms we're using a lot here. Every time I'm interacting with them, I have to take a lot of time to load back up all the state on it. I do have some docs that we'll be able to reference, but we'll talk about exactly what those things mean and go through that. But I just want to make sure that we can, yeah, that sounds okay. I just want to make sure that we can go through this flow here and also talk about exactly what is happening. Also, you can't see this because of my video, but up in the right-hand corner here, you're going to see running synth_design. So that's doing the synthesis. So it's taking the Verilog and going and synthesizing it. And maybe we should actually look at some of these resources. So like a really good project is, I think this is the, yeah, okay. So Mithro or Tim Ansel here is one of the best folks in the FPGA community. I believe works at Google and does a lot of amazing work. Also, you'll see that Vivado kind of steals focus when it's done here and prompts us for implementation if we want to. Before we do that, I want to hop back over here. So there's a lot of projects that Tim has worked on. SymbaFlow is the one here. So Vivado is proprietary. We're using the free version of it. So yeah, SymbaFlow is now F4PGA. And it is an amazing project, basically trying to make the open source FPGA toolchain here. Also, the new website is absolutely beautiful. And yeah, so it says it's kind of like a GCC, so a compiler framework, but for FPGAs. And you can see how it takes the HDL, so hardware description language, and then it has some synthesis tooling, and then various backends. So I think this is a great example here. So synthesis, Yosis is an open source project to do synthesis, and synthesis produces a net list. I need to double check that. Once again, haven't used this in a bit. And then FPGA, the tooling here, the backend is going to do the routing, which is basically taking the netlist and saying, hey, how can I put this on actual hardware? So you see there's some open source stuff to do it. And so we're using the Xilinx 7 series, the most popular Xilinx FPGA family. That just links to it. But all of these are supported. Actually, this exact board we're using is supported, as well as many others. And this is under the CHIPS Alliance also, which is a kind of like open source group. And as we go over here, let's take a look at how it works. Kind of the same sort of stuff. Okay, so this is like a very detailed view. So there's some kind of like higher level HDLs. We're just using Verilog directly here. Goes into synthesis. And I believe that. So I guess Vivado, it used to be that Vivado was still in the flow at some point. But I think NextPNR can actually, let's see, interchangeable physical net list. Okay. Cool. Okay, we're going to keep going through the Vivado stuff. Feel free to ask any questions here. Still trying to get an idea of what folks are interested in. Yeah, so it produced the net list. Maybe also let's just note that down. Docs. We'll look at those warnings in just a second. FPGA. Also, maybe I should have mentioned at the top, FPGA means Field Programmable Gate Array. So, let's say programming. Although program itself is a step. So let's say tool chain maybe. Synthesis. This is usually called place and route. That's why it's NextPNR is the name of the project. Synthesis, place and route, and what does Vivado call it? Maybe we'll say like programming. You're programming the FPGA with what's produced from that. So synthesis, produces a net list. And let's actually see if we can find it in here. I don't remember exactly where the things go out of here. Maybe we can discover that here. And let's look at these. Set property expects at least one object. Boards. Okay, yeah, so this is in our XDC file. I think this is because we are... It doesn't like something about this. Expects at least one object. Anyway, it looks like it did okay regardless. And let's go in and talk about file types. XDC is one, that's how we configure. And then XPR is another one. Vivado, XPC files. FreeBSD, XPC. This is actually a really useful guide, it looks like. Working with Xilinx. Wow, this is great. This is, I feel like this project is going to be a lot of link collection. FPGAs on OpenBSD. One of the things that you'll notice is that a lot of hardware stuff is done on Windows. And so like, I think that's why that guide that I wrote on installing Vivado on Ubuntu has done quite well, because like people, there's just not a lot of resources for it, because doing this development on Linux is not well supported at all. Oh, nice. Jonathan also tagged some folks like Tim, who I was just mentioning there, on Twitter. Thanks for doing that, Jonathan. Hopefully, I've had a few interactions with Tim, who I am a big fan of. I'll make sure to follow up on there afterwards. But yeah, maybe he'll stop in sometime and really school us on everything here. Because he is way, way more knowledgeable than I. Alrighty. So let's go back over. Let me switch something up real quick. All right, so we're gonna, there were 10 critical warnings. All right. So this is always really cool. So this is actually the background on my machine. But you can see the net list kind of like shown on the actual FPGA here, or the internals of the FPGA. And you can look at how the various parts of Verilog, so like the various modules, got synthesized onto here. So let's see if we can reload this. Also, there might have been an error down there at the bottom. Nope, that looks okay. So yeah, okay, it looks like it's using that XDC file. So usually I see things popping up here. So let's see It doesn't look like, oh, I might have to actually run I think I have to run the implementation for it to show up maybe. Synthesis is out of date. Sure, we'll rerun it. I believe that synthesis just finished, but, so once again, up in the top, it says running synth design. So that should be good. So this is how we're going to actually connect and look at what's coming through here. We're using a screen, just a tool that's likely already installed on your machine. All right, synth design is still running. What was the path that we were using there? Oh, TTY USB. Yeah, ls dev TTY. No, I don't want all of those. I only want the TTYs. Okay, yeah. So we have a number of these teletype here, and I think it won't show up maybe until we actually... I'm actually surprised that that is not showing up. Interesting. Anyway, we'll get to that in a moment. Okay, so it looks like route design is now running. That's what's in the top right-hand corner. So that should be good. Launched implementation 1. Cool. Open implemented design. Yeah. Okay. So after we run implementation, generating the bit stream is what actually gets programmed on the FPGA. And so, yes, I want to close the synthesize design and then open. Here we go. Okay. Yeah. So sorry about that. Synthesize design, right, is not specific to the actual FPGA we're using here, which makes sense from that diagram we were looking at from the F4PGA folks. So we generated the net list, and then implementation is, I believe that is the place in route here. Let's actually, what if I actually use the correct terminology, which I believe... Yeah, okay. Yeah, logical net list. Okay, this is the part that kind of can be confusing a little bit. Is there's net lists, there's two types of net lists, I guess. Like logical in this case and physical. I'm not sure if you heard that exact framing of it, but I think that makes a lot of sense. And so like one of them is saying, hey, like we've taken the Verilog and, synthesized it into a net list. And the next one is saying like, this is how it's actually going to be, put onto this specific implementation or this specific FPGA. So logical and physical net lists. Following stages. Okay, see, this is perfect. Nice. This is such good documentation. Really, really appreciative, folks. This is like the type of thing that I feel like actually is reducing the barriers, which I hope I'm doing as well. But they are miles ahead, doing some really, really awesome stuff. And it looks like they have. This is the old design here. Or the old thing that I was used to seeing. And here we can actually see Vivado in it. So they're breaking this into kind of like two different stages here. And so, yeah, I just want to make sure we document this really well. So synthesis, converting Verilog file to a net list. It's a draft of the final design. That's a really great way to put it. The synthesized model is a draft of the final design made with the use of available resources. behavioral level abstraction. Yeah, wow, great. This is just really great stuff. I really can't overemphasize how awesome this resource is. Let's see, where were we talking about FPGAs? We created that. Here we go. What do they call it here? I really like the way they're describing this. Design flow. The information below is a summary of the, let's see, the steps below are a summary of the, the more detailed content on in the F4PGA docs. So we'll link that there. Okay, produces a logical net list. Place and route produces logical elements. Yep, so place and route is saying this is for the target FPGA device. Needs to have information about the physical composition of the device, routing paths between the different logical blocks, and signal propagation timings. Nice. Four stages. They're saying packing, placing, routing, and analysis. And a lot of the reason why I'm adding this is obviously folks can go and just read this better documentation about it. But this is just useful for me personally to be able to write it down and also have like the quick refresher, you know, because I don't get to work on this every day. And I think most folks who consume won't be able to either. So let's see. Okay, so first it's taking all the primitives in the design. We talked about flip-flops. We didn't talk about muxes. We talked about lookup tables, though we can talk about more in the future. The tool begins a placement process. Physical location to every cluster generated. Documenting the bit stream format for different FPGA chips is one of the most important tasks in the F4PGA project. Could not say it any better. Oh, nice. And this does a great job of going through here. All right. We'll say this produces a physical net list. Although I really feel like there was a I feel like there's a term for what I'm calling a physical net list here, which I'm sure someone could be yelling at the screen right now. Place and route. Bitstream translation. Did this mention anything? Routing is an output file. Let's see if there's any other good resources. The Ultimate Guide to FPGA Design. That sounds really good. Design entry synthesis. This actually is pretty useful. Translate map, place routes. They use some different things. I like standardizing on what the F4PGA project is using, though. Let's see. Then the tool maps out the implementation by comparing the resource. You'll need to generate a bitstream file. Nice. Just gonna say reference. I don't really know what to call this quite yet, but I want to note down. I like the three distinctions there. Not really sure I'd call this the ultimate guide, but behavioral, functional, and timing. And it's associating these with yeah, so this is like what we're doing with Verilator. Functional would be I think this is also with like maybe the output file. We'll say cool. Okay, that sounds good. Let's get back over to Vivado. I do want to actually show stuff here. So we can see like the literal, I guess like variables, if you will, in our Verilog are shown here. And you can actually see them in here in the literal blocks. So this, I think this is super cool. I always love looking into this. So it's showing like both what elements of the FPGA are being used and also how they're connected together. So like here we can see that this is a LUT or a lookup table. Basically the way the FPGA works, right, is like we're not actually, generating silicon. Really what they're doing is it's having some logic elements in place there, and we're essentially like flashing like SRAM around it. And so it's that's what programming is. So it's basically, just setting hard coding, I guess you could say, in some memory inputs, which are going to then be used by these logic elements. So much higher performance than like executing code on a processor, but nowhere near also the capabilities of like actual silicon. I shouldn't say nowhere near. We could talk about performance at another time. But yeah, so you can really go in here and see like literal logic gates, which I think is just so cool. So anyway, despite Vivado's bad rap, it is really cool to be able to see this kind of stuff. Also, I wonder what you can do with the show cell connections. Wow, there's just a ton of information in here. Super neat. Okay. But we want to go ahead and generate the bit stream. And it does take it a minute after I click this usually. So basically one of the things that makes it difficult is like the most proprietary part of FPGAs is usually the bitstream format, right? The thing that the FPGA will actually understand. And that is what a lot of the folks in the F4PGA project and adjacent projects, like Yosis is, I think, now a company. And there's a lot of really important folks doing work on documenting those sorts of things. And then some vendors have leaned into it. So like I know, we'll come back to that. I know that, let's see if I can actually find, I want to give them a shout out. I always forget their name. Let's just go back to here. I want to look at the vendor. There's a vendor who has really like leaned into QuickLogic is the one that I believe all the stuff is open source. Or at least their bitstream format is. But a lot of folks have done work to kind of like reverse engineer it. Did want to give a shout out to the Yosis folks. They all have have contributed a ton. So yeah, Claire is one of the most prolific contributors to like the open source FPGA ecosystem. Matthew Venn does a lot of stuff around like doing well, he has this course here, and he also has like this open tape out thing where you can basically get your designs actually implemented in silicon, which is super cool. Anyway, these people are like top tier folks, and definitely have learned a lot from just kind of hearing them. Anywho, let's get back over here. Open Hardware Manager. So I haven't actually discovered, if you will, the board that we have plugged in. So I want to do that. And I think no hardware target is open. Let's try this auto connect and see if it can find it. So I think the issue is this cable I'm using to connect is only giving it power, because this is not the one I usually use. So let me grab another one here, which is why it also probably wasn't showing up on the device tree there. I know I have one around here somewhere. I need to get a placeholder screen for when I walk away from the computer. But I will be right back. All right, so it was literally right behind my laptop. I just couldn't see it. All right, so I'm just connecting it up now. Should be good. And all right, power coming through again. And no hardware target is open. It looks like something just changed here. Yeah, okay, so it found it. So that is pretty neat. Oops. USB 1. Okay, nice. So we can actually look at this as well. Yeah, so it's a character device, but what is the... Yeah, so we should... Okay, so here is really what we're going to be talking to. And you can also see some of my other stuff like my mouse and Apple Ink. I'm not sure what that is. Oh, actually, that's a dongle I have on the back of my monitor, I think. Yep, keyboard, all that sort of stuff. Cool. And so the FTDI chip is what we're actually talking to. And I was mentioning earlier using libUSB and how you like can discover some things. And one of the things I'd like to do here is actually start to move towards like writing some of my own software or our own software if other folks join this project to program things, really making it all like understanding the full process, right? So like how are the bits going from my host machine here to through the FTDI chip or first through like the USB interface to the FTDI chip, getting translated and using JTAG to actually program the FPGA. And we should definitely spend more time on JTAG. It is very interesting. And like I said, I always have to load state back up. And y'all can do that with me if you're interested in that kind of thing. Well, I'm not going to say typically a proprietary format. Anyway. So no hardware target is open. We'll do auto connect, which I think will find it. Has no supported debug cores in it. Okay. JTAG device index 0. So it did find the device here. And let's program the device. And I think that, so I'm using the, okay, so send, I'm passing in the send signal from top, and send is the 0 switch here. So it's going to be this top level switch, which we can hit to actually show stuff printing here. Or we should be able to after we program it. So let's program the device. I'm going to select the one that we have here. And it's using this bin file here, which is in our boards runs impl1. Let's see if we can find it actually here. Toolchain runs impl1. And wow, there's a lot of stuff in here. What is this? Okay, so we have our binary and bitstream files. I think that the bitstream file is, I don't remember the exact format, but it is proprietary and folks have been able to reverse engineer it. And then I believe what F4PGA is doing is providing kind of like an interchange format that's common across. So anyway, let's go ahead and program this. I'll stop boring folks with things. And so I'm going to program it, and it won't actually start doing anything until we flip that switch that basically says start sending. Write bitstream complete. So that's pretty fast, right? It's just basically flashing it onto the device. And let's see. This is where we are going to connect and listen over UART here, over a serial port, I should say. So nothing is happening, and this should, when I flip the top switch here, we should see it start to print, welcome to the MOS computer. Nice. So it did it, which is pretty cool, right? So that's essentially hardware that we created, and a UART module that is able to send that back to our host machine. Let's see. I don't remember if I think we did a reset switch as well. Yeah, reset, and let's see which switch we use for that. Reset is switch 1, so the one just below it. So let me open that back up. Oh, sorry. So if we do reset, and then let's see if it does it again here. Yep. So if we do the reset on off, then it will print again. I wonder if I just have reset on. Yeah, if I have reset just on, it's going to keep printing over and over again, which is pretty neat. So like, for instance, if we were like booting up or something, we could send some information across the wire here. So, and then if it's printing and I do stop, it'll print. And then if I turn reset off, it'll also stop, because it's not resetting each time. So that part is pretty neat to me. So let's go ahead and get a PR open that fixes this up. We're still only... let's clean up some of this. I'm actually gonna take this and just drop it over here. I was trying to do a some ASCII art. I'm gonna drop that over there. Obviously, I could just like stash it or something like that. But I want to go ahead and get a PR open to get this updated. And maybe we should talk a little bit about what's actually happening here. So to do so, maybe we can talk a little bit about UARTs. So this is a bit of a refresh for me. So we have these 2 wires, which serial, right? It means it's in order, right? And so it's sending packets across this wire, just like kind of any sort of communication. So, you know, whether you are sending TCP packets or you're sending, you know, just information like this over the UART, then there's a format, right? So that they know how to interpret things. And there's also a baud rate that we set to 9600 there. And yeah, and baud is bits per second. It's probably worth pointing out. And so essentially it's, you know, checking, I guess you could say, like how often to sample, right? Like when to when like the rising and falling edge of a clock is, right? Is the bit high or low? So the start bit, the first one that we send is to have, so non-transmitting mode is to have the usually called TX transaction high. So start bit pulls TX low for a clock cycle. So we're saying, okay, we're going to send some stuff now. 5 to 9 data bits. Data sent with least significant bit first. This is actually why I was having a lot of issues, because I was sending the most significant bit first. And then parity bits. So this is like an integrity check here, and then stop bits. So anyway, I compare this to a couple of other protocols here. And let's look at the actual RTL here to show what we're doing. So at the beginning, we have the clock count, and we're saying we want to, for this number of cycles, because we're using this baud rate of 9600, we're calculating how many cycles we need to hold a bit at high or low. So we're basically saying we want to send 1, so high. We want to pull the bit high, or pull the signal high, I guess I should say. Wait, so we want to pull it low to start sending something. So let's jump back over there. Okay, yeah. So that's idle, right? So we're saying pull it high if we are pull it high if we're not sending, if we're idle, and then hold it low to say we're about to send stuff. And then data bits, we are iterating through the transaction data and sending the bits here. So we're saying if it's less than the duration for which or the number of cycles that we need to hold the signal for, then just keep it as the data bit here. So we're sending ASCII characters here. So just hold that data bit. And then otherwise, we're resetting the clock count. So really a cycle count. If the bit index is greater than 0, then we're going to decrease it, right? So we're starting high, and so for a single character, 8 bits here, we are starting at 8 because we're doing least significant bit first. So we're going to decrease that, and hold that data bit. Let's see. If the bit index is greater than 0, yeah. So we're still sending, I guess, this character, right? And then if we have sent the bits corresponding to the character, then we want to increase the word index, or decrease the word index, actually, by 8. So I guess if we're visualizing this, it's kind of like, well, let's actually just... Maybe there's like a, let's see if there's a ASCII 2 bits. Okay, so we want to send the least significant bit first. So if this is the binary representation, we're saying that we are, let me take a look at this. Yeah, so our word index. So $247. How many characters is this? 33. I think the 247 might be left over from $264. I don't actually remember what the 247 is. I should definitely know that. Wait. 8 times 30 would be 240 plus 1. Okay, so 32 characters. Oh, I see. So, or 31 characters is really, I think, what we're doing, because these are being counted as 2 characters here, but really it's just a carriage return and a new line. So we're sending, yeah, least significant bit first. So we're basically starting at the bit index. I don't remember how these get translated. I think that was one of the issues I was having. So we're starting at the high end of the word index and the high end of the bit index, and iterating through that. Wow, I'm loading up a lot of state from whenever I fix this up. All right. Let's actually look at the... I don't remember if this actually... Let's see. Yeah, so this is a really convenient way to see what actual bits are coming through. So let's pop this back up. So we can see exactly what we're doing here. So this is the W, and we see it coming through. The tough part for me is always how Verilog is indexing these arrays, because I'm not super familiar with Verilog. Not enough information to feel like an expert by any means. I think I have some documentation on this. Verilog has kind of like a loose standard, you might say. We should talk about latches soon here, but ASCII array Verilog. Anyone who says otherwise is wrong. Okay. Yeah, a lot of people suggested starting with 1, and I definitely like the 0 indexed a little better there. Okay. So I really want to logically work through this. Because we're obviously sending the W first, and it makes sense to me that we'd send the least significant bit of the W, but I don't remember why the word index, which is like the total number of bits. So we have the total number of bits here, and then for each character, we're sending the least significant bit first. But I don't remember why W is... This is why I had it in reverse, actually. I don't know why W is at the end of the register here. So if anyone has information why Verilog represents it that way, definitely would be interested. But anyway, let's go ahead and get this up. So this is working correctly. And is there anything else that we really don't need to change this? What was the diff here? Oh, MOS comp. I actually do want to change that, but I don't want to put the ALU in here yet. That's fine. Oops. All right. Let's see. So we want to update these two, and then I was going to bring this as well to fix the path. Cool. Get status. What is the diff in the top? Add note in top.v about timescale formatting. Adds a note about how timescale is represented. RTL UART. One of the nice things about like doing this kind of like full stack project is you can kind of like move up and down things you're interested in. And if we decide on a common interface, right? So like, let's say we're saying this is going to be a RISC-V CPU, then I could actually start working on like operating system level things as well. And I want to have the freedom to do that. Like, you know, why do we have projects that we work on the side, right? If we can't have some freedom to like explore the things we want to. So anyway, I fully intend to do that. I hope that's okay with everyone. I remember discussing, I can't remember if I wanted to make a note about this, but the fact that we use the UART RxD as our send, I believe that it's labeled this way because, so like on the FTDI chip, actually, let's just use Excalidraw because if you know me, you know I love, love, love Excalidraw. I also like dark mode. Okay, so on our board here, and I should open up the... Okay, yeah, so this is a really good diagram. So the UART here is talking to the FTDI chip, as I mentioned. And so let's say this is FTDI. I'll zoom in a little because I know the quality isn't the best here. And this is the Arctic 735T here. So maybe if we do like this, and no, I want it to be filled with. So I believe the reason why it's labeled as the RX. So we have like RX and TX, right? But on one side, let's use a double-sided arrow here. It just depends on like what side you're looking at, I guess, is the point I'm trying to make. Because on one side, the RX, the RX for one is the TX for the other, if that makes sense, right? So I believe that we're sending on what is denoted as the RX here. the RxD out is because it's referencing that it is the, actually, this is not accurate. Well, that one was accurate. Sorry. This is the Rx here, but the Rx for one is the TX for the other, right? So we've implemented it going one way, and yeah. So it basically looks like this, and I believe why it's labeled that way is it's like, hey, this is the RX for the FTDI chip. It's labeling it as RX for that. So if you want to send things through the FTDI chip, which can do this kind of like USB UART translation here, which maybe we should also say how that's getting into the machine, although that's a little more opaque to me. But let's go ahead and take a stab at it. So it goes through, and then let's say our host machine over here has a USB connection, which this is going to be more rudimentary. But essentially what's happening is we're doing UART between the FPGA where we've implemented the design, right? It's saying like, okay, I know how to send things. And we've just hard coded this message like in the hardware essentially. And then it gets to the FTDI chip and it's like, all right, I know how to translate this UART signal into USB, which then we're able to consume. It's a pretty nice diagram. Maybe we'll like post that along with this stream or something. All right. We'll label this as FPGA. Laptop, I guess. I think I can update the thumbnail after this. And welcome to the Moss computer. Is that the message we were sending? Let's see. Fix UART transmission. Fixes previous behavior of sending messages over UART in reverse. So what we'd like to be able to do here is actually be able to like, you know, talk to it. I'd like to implement receiving over the UART as well, and then we can have like you know, an echo kind of like server or something like that, and we can show that kind of like bidirectional communication. Yeah. Update. I'll just say this path. Another thing I want to mention is if folks have other boards that they want to try this on in the future. If people like, I'm not asking for people to send me things, but if you do send me a board, I will work on making anything we do work on it as well, which could be kind of a fun experience as well. So let's push this up, and we'll have gotten some work done. Just say this. And we do have some workflows set up, but they don't really do too much right now. Also, I recognize that I'm the only reviewer here. Where do we have that output? Oh wait, it was over here, right? Nope, it was. Nice. All right. Let's see. I also wanted to do some work on that ALU and potentially update some simulation. So we do have some simulation of the ALU itself. So when you run Verilator, it is basically producing all of this stuff, basically just doing a bunch of code generation. And it allows you to do some really cool stuff like produce waveform if you run it. So for instance, I know in the kind of like single step, yeah, this, I think that's eval. Let's see, TB. Yeah, so this data.vcd. And let me see if I actually... I believe that the Verilate here is... So yeah, you can see the same sorts of things. So I think we're just confirming that it actually does run, or it does generate. And right now it's not actually doing anything, right? It's just exiting immediately, which is not very helpful at all. Also, I noticed, yeah, talking about how like this has been around for a little while. We've got the 2020 on here. 2 years ago. Yep. Nice. Cool. Alrighty. Apologies for some of the sniffles there. I've had a little bit of allergies here. Trying to decide what I want to work on next. So I guess like one of the things that I feel like would be a good POC is if we could send some instructions basically over UART, which I know this is like not the how you'd normally want to do things, but if we could send some instructions over UART, perform the calculations in our CPU, and then send the result back, basically, like execute instructions on them. I think that would be a pretty cool experience, which we could work towards. But anyway, yeah, so I think that would be cool. Maybe we could talk about JTAG a little bit. So the reason why I split this out into its own document from protocols is because JTAG is not a protocol itself. And let's actually look up some documentation. Like I said, I frequently have to go back. So it's not the name of a protocol. I frequently have to go back and kind of like load up state on JTAG to understand exactly how it works. So let's just go and see what we find here. So I have mostly found jtag.com to be very unhelpful. So don't really recommend it for getting information. This XJTAG. So yeah, the in-system programming. This is actually pretty useful here. Also, I want to be consistent with how we're presenting resources. So resources at the top here. JTAG explained. Yeah, let's move this over. Whoa. I guess this is, let's see if it. Oh, no. I guess we just need to drop this in general. Wait. I meant to be, let's see. FPGA for Fun is a pretty cool site as well. Yeah, they have a number of really cool documents here on various interfaces. So we're going to drop this one. Sorry for the person who wrote that. What is JTAG and how can I make use of it? Say notes. Nice. Okay. 4 pins plus 1 test action port. You'll see this a lot as well. The test action port is referring to the pins, which are defined here. Yeah, so essentially what you're doing is controlling the state machine, and I really want to be able to find the, I think that it was that, well, actually, let me, I think it was that post that is no longer there, but it had a really awesome diagram about exactly how this works. This one is actually pretty useful as well. Oh, I like the way that it steps through this, like talking about the issues with if each of them are all connected together. So like, okay, so you have CPU and FPGA. ICs are connected together. Excuse me. A few thousand on a PCB, right? So like on our dev board here, right? There's traces all over it. You probably can't see it super closely that are connecting these various integrated circuits, like the FTDI chip and the Arctic 7, the actual FPGA on here. And so you need to test them. So JTAG was created. JTAG control or hijack the pins of all the ICs. On the picture, maybe JTAG is going to make all the CPU pins outputs and the FPGA pins inputs. Then by sending some data from the CPU pins and reading the values from the FPGA pins, JTAG can make sure the board connections are fine. Okay, so this is actually not a like frame in which I've looked at this much before. But really what it's saying is like ignoring, or my interpretation of it is ignoring like the actual logic gates that are implemented in here or in each of the integrated circuits. I just want to make sure that like when I send on this pin, it's received on this pin. And that's obviously really useful to be able to do. JTAG can do a lot more, so I'm guessing this is about to tell us a little bit more about that. So our host machine here has the 4 signals, and there's also that optional reset one that looks like they don't call out here. Need to be wired in a particular way. So all TMS and TCK are wired in parallel to all JTAG ICs. Okay, this is actually really useful. I'm gonna add this as well. I don't know why, I just really enjoy this kind of stuff, like learning physically about what's going on here, and then taking like a board that we have, for instance, and applying this to it. Okay, so they're in parallel, right? So if send a signal on it, they're all going to receive it. TDI and TDO are connected to perform a chain. Okay, so we have our various components down here, so like our ICs, and no matter how many you have, it sounds like you have, yeah, so in and out. So there's only one. Okay, cool. This is a great explanation. You know, I feel like when I'm not doing this on the stream, I really kind of struggle with this. And so I'm really glad to be able to do this, honestly. Okay. No, I always guess the wrong side for these. So this would be TDO. once again, may be obvious for folks, always helps me to draw this out a little bit. And so we're just going to have a bunch of these. Host. We'll say IC1, IC2, IC3. That was not the best connection ever. TDO. TDI. TDO. TDI. And then so that's what we mean by, so like JTAG chaining, you might say. Okay. So they all get the clock and the, let me double check what the TMS signal is. Test mode select. So it's the control signal, right? So what do we want to be happening, right, in these various components? Three outputs and one input. Right on. Okay. Okay, so 3 outputs and 1 input for the host or the PC here, and then really 3 inputs and 1 output for the integrated circuits. So they need to wire it a particular way. As you can see, each JTAG compliant IC has 4 pins used for JTAG. 5th pin named, okay, so they do mention the JTAG reset. All big ICs use boundary testing using JTAG. Boundary testing is the original reason JTAG was created. Nowadays, JTAG configuring using JTAG. So debug. So really, it sounds like we have 3 use cases, maybe. So boundary scan was the one we were just looking at. In-system programming, I think these are from the other resource we had there. Yeah. Software debug. So software debug, I think, is a key part here. JTAG was originally created for boundary scan. Is that like boundary scan testing? Would that be an accurate way to say it? Yeah, boundary testing. Let's say just boundary testing. I like that. The boundary scan is a process of testing that individual ICs in a larger system are wired together correctly. It generally consists of verifying that sending a signal from a port on one IC results in that same signal being received on another, it bypasses the logic implemented in the ICs under test. Okay. So let's look at the other cases. I'm just going to get rid of this for now. The tap was designed to interact with new registers that were added to devices to implement this method of testing. Very quickly, however, silicon manufacturers recognized the benefits of using the tap to access registers, offering other functionalities such as debug and programming. The main register added to a device specifically for JTAG testing is called the boundary scan register. Okay, yeah. So in the individual devices, we have these like boundary scan things. It was basically like an interface, right? It's saying like, hey, you can control these, and I'm assuming like sample on them, and that's how, like, if you, like, back to our example here, if we're testing the connection between these, if you have registers that basically say like, this is value here, let's sample the value here before it actually gets into the core part of the IC. Have we mentioned the boundary scan register? My wife is texting me asking if I'm alive. I better respond. Also, our puppy has been a little feeling a little under the weather. I'm live streaming right now. Maybe she'll go on YouTube and watch me. Let me also check the chat here. Isn't JTAG like mostly closed, similar to ISO? Hey Daniel, thanks for stopping by. When you say mostly closed, do you mean like as opposed to like open source, or like closed loop? I guess. I'm guessing since you mentioned ISO, it's mostly closed. Like, yeah, I think from like that perspective, I think JTAG is not like something that is a open standard. I guess. Well, I don't really know how to define that, but yeah, maybe you have a better idea than me. So feel free to let me know, or let everyone know. Actually, thanks again for stopping by. Also, I'd like to link to these. Or maybe you mean close like it's not changing now. Battery equipment. Maybe my docs here are 1149.1. Yeah, they are just totally wrong. Yeah, I meant like it's not openly accessible. Yeah. So also, so I've seen like a couple of folks like I bet people who would be interested in this stream would also like follow Foone on Twitter, Foone, and they frequently do like interesting hardware things. Yeah, hi Daniel, thanks for stopping by. Also, I like your emoji. Is that a turtle? I like it. Yeah, so like folks that do a lot of hardware stuff, like will frequently crack something open and be like, oh, I found like the pins. So like the 4 pins we were mentioning there. When you see that, you know that you might have an opportunity to like do some interesting things with a device that the manufacturer was likely not intending for end users to be able to do. So you'll see some interesting things there. And I read some stuff about how manufacturers, right, you want them there for test, right? It's kind of like this dichotomy. You want to be able to access these low-level things for being able to test them out. But then when you send them out, you don't want, users to be able to test them. And so, sometimes they'll do like creative things like, like destroy the connections of the JTAG pins or something like that. After they've verified that the system works correctly. But yeah. Also, Daniel, I totally agree. I have struggled a lot with JTAG, which is one of the reasons why I'm like back here looking at it again. So yeah. Standard test action port. Though I'm not really sure I'm saying that correctly because JTAG just not let's see. Hey Verneri, I hope I'm getting your name correctly. Thanks for joining. They say the IEEE spec is a very nice resource, but it's quite pricey if you don't have the academic access. At least I haven't found any good resources online besides the spec. Yeah, echoing that same sentiment. So I think this really belongs. I think the IEEE is test action port. Or test access port, sorry. Trying to determine if there's like the interesting. Cool. I think well, I know that test action port is codified there. So it's more correct than it was before. Still don't know if that's totally the best way to state that. But anyway. Okay, so boundary scan cells and their functional mode, they have no effect on the operation of the device. This is the mode in which they operate when the board is running normally. So they're basically just like these boundary scan things are just pass through essentially in normal function. They can be used to control the values being driven from an able device onto a net and also be used to monitor the value of the net. This is like a lot like tracing, which is more akin with what I do day to day. Disconnecting the control of the pins from the functionality of the enabled device makes boundary scan test development significantly easier than the traditional functional test, as no device configuration or booting is required to use the pins, right? So you don't have to put software onto the device to be able to sample it, you can just have this separate system that's just like testing the edges of kind of all your ICs. Maybe I might write a blog post on this, because like I feel like and like kind of expressed by folks on the stream as well, I think that there is a better way to describe this. Maybe, I don't know, maybe that's arrogant of me to think that I could do a better job, but I do think there is at least lacking resources. So anyway, there are two main ways that this boundary scanning capability can be used to test board. First way, connection testing gives good test coverage. It is based purely on the JTAG, right? So that's saying like, these two things are connected to each other. Second way extends the coverage by using a JTAG-enabled device on a board to communicate with non-JTAG peripheral devices, such as DDR, RAM, and flash. Okay. So we already read about the connection test. Nice. What other devices are not JTAG-enabled? BSDL. Let's note that down. The boundary scan description language BSDL is used to define JTAG configuration on specific devices. Cool. Okay, so this like mentions the other, but I really would like to see like this is obviously interesting to me, but in the context of FPGAs, like we're really interested in programming using JTAG. So JTAG for, sorry about that. JTAG for programming FPGAs. Also, another thing I want to mention is like when we program our FPGAs, frequently you can either program the FPGA directly. This is something I definitely want to produce some documentation on. You can either program the FPGA directly, or you can program some memory that it has access to. And on startup, the FPGA is going to load that from memory. And that allows you to have like a persistent thing. So I don't have to, like, as I have it right now, I just put it directly onto the FPGA. And so I have to be connected to be able to do that. If I flash into memory, I could just take this and like plug it into a wall, for instance, for power. And then like, let's say like send something over the Ethernet port or something like that. So anyway, I think that's important. So the Digilent docs have some stuff here. Also, I almost always say diligent instead of Digilent. Wow, these are very, very minimal. I really don't find these super useful. JTAG programming guide. Huh. Oh, this is from Xilinx. So this is pretty neat. I'll add this to the resources. Xilinx JTAG programming guide. Also, just wanted to I have the chat open here and wanted to encourage folks to go check out Daniel's streams as well. Does a ton of really cool RISC-V stuff. Trying to get on Daniel's level with my streams here, just getting started. Definitely check those out. I think they're on Twitch. I definitely enjoyed tuning in a couple of times and need to find more time to do that. So awesome work on those. Cool. Hardware. I see. So this is using, so like also you can see we're providing power here as well, because if we're like just using JTAG, and maybe I should mention this as well. Let me see if I can find it. I'm trying to find the ports here, but you can do JTAG over like the FTDI chip that we were mentioning. But then there's also, you can get a JTAG programmer and connect it up to this board as well. Oh, wait, here we go. So there's like a separate JTAG port with this 6-pin JTAG header, which, if I could find it, that would be helpful. Maybe if I go back up to the board picture here. 10 buttons. 11, 12. I'm actually going to look that up. I think it's just right in front of my face, but JTAG port. Oops. This is exactly what I was looking at. I think there's something in here. I remember looking at it. Power supplies, JTAG header. Oh, this is a good description of the USB UART. Anyway, there are headers where you can basically use JTAG as well. Actually, let's just search that. Yeah, so I don't actually have a I guess I'm like not trying to do anything specifically. I mostly just want to be like very clear about like how folks can program this board / use JTAG. So it's more just knowledge gaining, I guess, right now. Comment for JTAG. Port J10. Okay, so that actually should help us out here, I think. J10. Which one is the J10 port though? Anyway, it's not really that important. You can use a JTAG programmer through that as well without using the USB UART bridge. Okay, so actually this is really useful. This is what I was drawing earlier, right? Like the RxD, which is labeled in the config file, is the RxD for the FTDI chip, this FT2232. And that's why we're sending on the receive port, if that makes sense. Okay. Actually, this is not really super useful in my opinion. Let's look at the Stack Exchange answer. So I think there might be something in here also about programming, but it's just kind of a so okay, yeah, this is really what I wanted to get to. That I think is really neat. Like one of the coolest parts. So if you are doing the if you want like the long-term programming, right, that you can use this without having to be connected, and you know, for it to survive reset, I guess, then the way it does it is it still programs the FPGA, but instead of programming the FPGA with your design, it programs the FPGA with a design that can program the flash device that's connected to it, and then it uses that hardware to program the SPI flash here. So if we look at this, essentially, I think 20 here, or no, 18 is our flash memory. So that's where we would store our design. So essentially what happens is it programs the FPGA with a circuit that knows how to program flash memory. And then it uses that circuit to program the flash memory, which I've always thought was super cool. And definitely something that is like interesting about programming them. So anyway, that's really what I wanted to point out. Yeah. I would like to get maybe like some more information on using JTAG to program a device. I wonder if there's just a good example. This is everything on jtag.com is like, this is a sales pitch. It's not really very helpful. This looks like it's specific to. This is what I'm talking about, where we need just like more open source stuff around this, which maybe I'm not right being very specific about what I'm looking for here. Really, I'd want like a bit by bit definition of, or an example of how programming a device via JTAG works. I don't think I looked at this one. Okay, so this is this state machine is really, really useful. Really useful information. So let's actually, maybe I can get an example of that and we can talk about how this works. JTAG state machine. Ooh, yeah, All About Circuits kind of has some good stuff usually. Yeah, okay, this is good. The tap state machine. So this actually turned out to not be very useful at all. Oh yeah, Daniel says that everything looks like a sales pitch is uh, the example of it all feeling like very closed. Yeah, I don't understand. I mean, like I guess it is like sensitive in terms of like uh, they don't want folks like basically folks outside of the people manufacturing the device aren't supposed to be using it, I guess, but it makes it very close to people who don't work on that. So anyway, um, oh nice. Let's look at this introduction too. Oh wow, this is probably the best thing that I found so far. What is this called? Let's see, Introduction to JTAG. JTAG and the test access port. Oops. Wow. Yeah, this is a really good article here. An instruction register, several test data registers, in addition to some glue logic. Common JTAG instructions. So recommended instructions. So I think like the kind of like theme here is that you can do anything with the JTAG or the test access port state machine. But there are some like common things. So let's look at how this would work. So we have data register and instruction register. So like pretty common with folks who are familiar with CPUs or any sort of, I guess, logic. TMS equals 0 to, yeah. To understand these states, look again at the JTAG system from the previous article. Capture, shift, and update states. Oh, nice. The Blackmagic probe source. Should have thought of that before as well. In application debugger for ARM Cortex. Yeah, this is super cool. Yeah, and you'll see how it's interfacing with GDB here too. Okay, so let's look back up at this. Instruction register, test data register. Nice. Okay, so like TMS we can see is controlling this. So select DR scan. This can kind of pass through. Parallel load test data into the current data registered, specified by current instruction. So, okay, so capture data register. And then you can exit the data register. Latch data in register. Gotcha. So we're essentially just like sending stuff around. I think that this source code is going to be super useful. Oh, true. GDB main. This is pretty cool. Write single register. Target reset. Command. Scan JTAG for devices. I know this is riveting to watch here. Yeah, I guess like I really want to produce a like example of like literally bits, you know, going from the host and yeah, showing them going from like the host and into the JTAG circuitry and then like doing something. So load remote target. This is all focused on ARM, which is interesting. I feel like I'm losing steam a little bit. Might need to come back to this. I am intrigued though. RTT control block. This is kind of useful. Shift register bank in the instruction register parallel loads a pattern of fixed values on the rising edge of TCK. The last two significant bits. This is, oh, this actually is different. Okay, this is a good one. I'm gonna add this too. Okay. All states have 2 exits, so all transitions can be controlled by the single TMS signal sampled on TCK. So that's pretty neat, right? With this single signal, because every state has an exit from it, you can have one signal control them all, right? Because you can always just exit that state. Two main pass allow for setting and retrieving information from either a data register or the instruction register of the device. The data register operated on depends on the value loaded into the instruction register. Boundary scan instructions. Bypass the instruction causes the TDI and TDO lines to be connected via a single bit pass-through register. The instruction allows the testing of other devices in the JTAG chain without any unnecessary overhead. Okay, so we'd want to put like jumping back. Okay, I feel like I'm gaining some steam again. Jumping back to here, we'd want to put like, let's say we are testing this one. I think we'd want to put these two in the bypass. Yeah, we want to put these in the bypass state. Or bypass isn't a state. It's an instruction. So this instruction causes the TDI and TDO to be connected to the boundary scan register. The device's pin states are sampled with the capture DR JTAG state, and new values are shifted into the BSR with the shift DR state. These values are then applied to the pins of the device using the update DR. Okay, this instruction calls TDI and TDO to be connected to the BSR. However, the device is left in its normal functional mode. Okay, so this one seems, so this is like more software debug, right? So you can say, oh, I just want to know, like, it's kind of like a proxy, right? I want to know, I want to know what data is flowing through. Signals, let's say, instruction. Instruction registers. And we just have one, I guess. So this is kind of weird, but I like it for the symmetry. Instruction. The instruction registers, there is only one. Instruction register. And I like the way this is worded. Holds the current instruction, which informs how to pass data from the data registers. Oh yeah, Verneri mentioned the RISC-V debug spec. For a bit, I actually worked on that with some folks, although I totally fell off. Tim Newsom from Sci5 was, I think, leads that and was super helpful. And I ended up not really being able to commit as much time as I wanted. But yeah, really, that is really helpful. I agree. Actually, I'll pull that up here in just a second because I think that's really useful. I have all the specs here on my machine. Here we go. Where is the debug spec? I definitely have it here somewhere. Oh yeah, RISC-V debug stable. JTAG TDR. So you were mentioning the transport module, yeah. It's probably good to keep it big. Let's see. JTAG background. Okay, yeah, there's some really useful stuff here. I kind of forgot about this. Oh, nice. The TDRs. Reserve for future RISC-V. Yeah, this is super helpful. Thanks for mentioning this, Verneri. Yeah, TDR, test data register. Nice. I feel like well, yeah, I should definitely use this as driving a lot more of the JTAG stuff. This is a great resource. I had not looked at this in a long time. I do like how this defines them as like separate. Like I feel like the listing here, well, so there's like the instruction register and the data register, and then the DTM tap registers. I guess it's like a little confusing for my brain, I guess, that like they're both defined as registers when really these values are kind of like loaded into registers, I guess. Although I guess it's conceptual, right? Because here, like these don't necessarily uh they're not necessarily like separate things, I guess. Well, that's really not super accurate either. I'm going to note them down here though. Well, I guess they are. So, okay, this actually makes sense. Really, these are, it's just like there's an instruction register and there's a data register. So that makes sense. All right, there's an instruction register and then some data registers that are like saying, hey, get this out of this data register. Um, okay. I guess it's calling BSR probably uh, the data register in this case. Okay. So, okay, that's a great description from Verneri. You can think of the IR as an index that selects which TDR to place between TDI and TDO. That is, I'm going to just put that in a quote here. Also, this is the first time I've met Verneri, who seems to be very knowledgeable here. So thank you for all this information, and would love to chat sometime. Seems like have a lot to learn from you. You can think of the IR as an index that selects which TDR to place between TDI and TDO. And let me give you some attribution there. Awesome. Thank you so much for that. That's a really, really helpful framing. I see. And so I think, so it sounds like that, yeah, so the data register, yeah, so selects which TDR. Okay. Awesome. Okay, that makes a lot of sense. If I use the framing that you suggested, I actually understand, which I should do. Nice. Thank you again for that. Oh, nice. Came to the stream by Daniel's retweet. Well, thank you for retweeting, Daniel, and thank you for showing up, Verneri. This might seem, it sounds like you have some great experience, so this might seem like amateur hour to you, but definitely will continue to improve due to folks like yourself. Let's see. So yeah, so this is basically saying, so this would be allows incoming data to be, yeah, allows incoming data to be passed without modification to output, used when IC is not under, used when, let's see, what would be a good way to say this? Maybe there's a good bypass. Is bypass defined here? Yeah, bypass here. Yeah, is used when a debugger does not want to communicate with this tab. Cool. So it's basically saying, yep, this data is not for me. I'm going to pass it along. Okay, ID codes. So, okay, cool. So it's identifying this. I guess it's just ID code together. Yeah, I'm gonna go with this definition. Nice. Okay, so ID code is saying this is information about the device. JTAG can be used to monitor I feel like I don't have great definitions for each of these. Maybe this, I mean, I got these originally from here. Also, like, the Wikipedia page is probably pretty good too. Or maybe, oh, okay. So this is nice. Today, JTAGs use a primary means of accessing. Also, let's put this in the doc as well. An in-circuit emulator, use JTAG as a transport mechanism. Okay, we can probably get something here. So we're really saying when we're saying software debug, we're saying debugging using software. Can be used via yeah, I'm still struggling with the wording a little bit. Yeah, there's probably gonna be some room for improvement here. In system programming, is that? I don't know if that would fall into the same category here. Yeah, I think that falls under this category. All right, let's see here. Because JTAG enables writing data to memory, it can be used to program devices directly or program flash memory through a debug enabled device. So I guess like what I mean by that is like you can, I guess essentially what it says, you can use the same data bus that the CPU uses to be able to program. So I think that kind of makes sense. Then this yeah, and I have this description of bit banging, which I think actually doesn't necessarily belong in the JTAG documentation. Did it used to be over here? Let's just keep it separate for now. Not gonna push it up, but I am gonna move. I think I'm gonna push the JTAG updates because I think this is useful, so hopefully. Drop that one. And then I'll add a link to the and I need to find Tim Newsom was a very, very helpful person and has pretty much owned the debug spec, which is super cool. Docs, and I want to do protocols and JTAG. Move JTAG to dedicated docs and add content. Moves the JTAG documentation to a dedicated doc and adds additional content. JTAG itself is not a protocol, so it does not belong in the protocols documentation. I feel like it does. Well, no, it's not a protocol. Yeah, okay. There's lots of things that say it's not a protocol. I'm like, well, I guess it depends on how you define a protocol. Let me open up the repo again. Whoops. And we'll go ahead and round out with this one. We're just about at 3 hours exactly. That seems like a pretty good stopping point. Let's see how this renders. Does it look okay? Awesome. Cool. I love this so much. This is so helpful for me to understand, at least. Nice. We'll go ahead and create that pull request. I need to do a gate on the Verilate to check if it's just like markdown changes. Anyway, cool. I feel like this was a good first stream. You know, I definitely learned a lot or refreshed a lot in some cases. Definitely appreciate folks stopping by. I'm going to write up a blog post like kind of codifying the motivation for making these streams, as well as hopefully a vision document on Moss. And yeah, I hope that this continues to be useful for folks. And yeah, feel free to reach out on Twitter or anywhere else you can find me. Check out the repo on YouTube or on GitHub, sorry, if you want to. Feel free to open issues or things like that. Since the vision isn't defined super clearly quite yet, you know, we'll see how much issues are considered at this point. But the original motivation for Moss was kind of defined here for a vertically integrated computer, right? I really want to have from like the hardware up through all of the software. So like if we need something to, you know, something that impacts user space or what we're able to do in user space, we should be able to go down to the hardware. And so I want to be able to do that, have that, but have it in a very understandable way. And that's why debug is so important to me. It's not just important in like understanding how to build the CPU, but actually in the CPU that we build, I want debug to be like first class and really important. And I don't want to sacrifice performance in that. So kind of the idea around doing that is building a lot of our own tooling to support debugability and having, you know, a well-designed kind of like places to plug in for debug. So anyway, a lot to decide there still, but definitely appreciate folks stopping by, especially Daniel and Verneri. Thanks for y'all's input and expertise. Yeah, Daniel says, can't hear Moss without thinking of Moss from the IT crowd. Yeah, that's a good call out. Maybe that's another side reference that it makes, but cool. All right, well, I'm going to sign off for the day. Thanks for sticking around, and if you're watching the replay,